Good morning, good afternoon, and good evening, everyone. Thank you very much for joining us today for our Decision Analysis Society webinar. And my name is Shufi Liu, and I will be moderating this session. Before we begin, just a quick reminder, today's webinar will be running for about an hour. And we encourage you to stay engaged, and there will be opportunity for questions at the end of the talk. So now it's my great pleasure to introduce today's speaker, Professor Jose Correa. And Jose is a full professor in the Department of Industrial Engineering and principal researcher at the Center for Mathematical Modeling at Universidad de Chile. And Jose's research and his contribution have been widely recognized. He has received many awards, including the ACM SIG Com Best Paper Award, and the Informs Transportation Science and Logistics Best Paper Award, and Turker Prize finalist recognition, and research awards from Amazon and Google, among the others. And beyond his scholarly achievements, Jose serves also the academic community as an editor for leading journals such as Mathematical Programming, Series B, and Mathematics of Operations Research and Operations Research. So currently, he also serves as Vice Rector for Information Technology at the Universidad de Chile. So today, Jose will be presenting his recent work on monotone randomized apportionment. And let us welcome Professor Jose Correa. And Professor Correa, the floor is yours.
Thank you, Jufei. Thank you for the for the invitation. It's a pleasure to talk in the Decision Analysis Society at Informs. And I will be presenting some recent work that appeared in EC last year, and it's under submission to OR, on a topic that I think it's relevant to decision analysis, and it's relevant in political science also. So let me try to tell you what this is about, the paper. I will try to give a lot of examples and mostly grasp ideas through examples. But I should start mentioning that this is joint work with some great colleagues, Paul Golds from Cornell, as an assistant professor at Cornell, Ulrike, who is an assistant professor also at TU Eindhoven, and she was in Chile for some time as a postdoc, Jamie, who was a student. Most of this work was done when Jamie was a student, a PhD student at Harvard, and now he's an assistant professor at Yale, and Victor Verdugo from the Catholic University in Chile. So let's get started. So first of all, the first question is, what is this apportionment problem in politics, in political science?
So Jose, I'm sorry to interrupt. Would you like to share your slides?
Share what, sorry?
Your slides.
They are being shared now, no?
Shafe, okay. We can see them. I can see them.
Sorry, yeah.
I can see the slides.
Is it good?
Yes, it's good now.
Okay, great. Thank you. So what is apportionment? Apportionment is this process under which, for instance, in the US, you allocate a certain number of seats in the House to each of the states. And according to the Constitution, this should correspond to the population of the states in some way. What does correspond mean? It's not an obvious question, as I will try to express here. But essentially, what we have is a bunch of real numbers. In this case, I'm thinking of the populations of the different states. And we want to round these real numbers to integers so that their sum is some number, 550 or whatever number, which is I want to preserve the sum in some specific way. So this is the process under which you allocate seats to states for the House in the US. Also is the process under which you allocate seats to parties, to political parties in Chile. So in Chile, we have districts. Each district has a number of seats. Then parties compete for these seats. They get a certain number of votes. And then there is a process under which this number of votes is translated into how many seats each party gets in each district. This is done not only in Chile, but in many, many countries. So basically, I'm thinking of two options. So I'm thinking of parties getting seats according in proportion some way to their vote share, or I'm thinking of states getting seats in proportion to their population. So, but both problems mathematically are the same problem somehow. Okay, so this is the apportionment problem. So basically I have some real numbers that I want to round to integers so that the sum is some pre-specified number. So let's think of an example. So let's consider an example in which I have a house that I want to fill, and there are 11 seats in the house. So there are 11 seats, and there are 6 parties. And each party gets some number of votes. So we have colors for the parties. So party 1 gets 110 votes, party 2 270, and so on. Now, how are we going to split these 11 seats into these 6 parties? And there are many ways of doing this. In many countries, in most countries, what they use is what's called the don't method. In the US, for assigning seats to states, we use the Huntington-Hill method, but there are many options for this. And one natural number that we want to look at is what is the party's deserve, how many seats a party deserves. And if we think proportionally, what the party deserves is this number that I'm going to call QI, which is basically the vote share, the number of votes divided by the total number of votes, times the house size. So in our case, this house size is 11. This number for party 1 is whatever number of votes it got, and the total number of votes is just the sum of the votes, right? So if we can compute the shares of the parties for all parties, and we say, okay, party 1 has 1.1, party 2 has 2.7, and so on. And this would be sort of the ideal proportional representation. However, these numbers are not integers, so it's not obvious how to round them. What is the right way to round them? And there are methods, and let me try to explain one of these methods. So one thing that one would like, and this is not true for every method, but it's going to be an axiom during my talk, is that I want that everyone gets its quota. So what does this mean? It means that each party should get either the floor of its QI or the ceiling of its QI. Okay, and maybe sometimes it's going to get the floor, sometimes it's going to get the ceiling, but not below the floor and not above the ceiling. Okay, so this is one axiom which we call quota. Sorry, this is repeated somehow. So now what we do is that the first step in any allocation, in any apportionment method that satisfies quota would be to say, okay, so party 1 will get at least 1 seat. So this is fixed. Party 2 should get 2 seats, at least. Party 3 also 2 seats, and so on, right? Everyone is getting its floor. And now the question is, how are we going to split the reminders, the residues? So PI in my talk is going to denote these residues. So these residues are just this fractional QI minus its floor. And now note that these residues, which are these PIs, sum up to some integer. Okay, in my case, since the house was of size 11, and I have already assigned 8 seats, my K will be 3. Right? Okay, so what can we do now? Classic method would be to use Hamilton's method. So what is Hamilton's method? It's very simple. You look at these reminders, at this, basically these distances representing the different PIs for all the parties. And you select the largest 3. Good. So this would give you some allocation. I guess in this case it's going to be this one, and this one. those three parties will get a seat. However, this has some problems which arise when we want to impose more conditions. So the first condition we are imposing is quota, fine. But now we want to impose some more natural axioms. One of them refers to monotonicity. So this is why my talk is called monotone randomized apportionment, because this method, Hamilton's method, fails what is known as population monotonicity, which is sort of a natural axiom. So the axiom says that if I have two parties, so look at the red and the orange party now, the red and the orange. Now, under this situation, under the original situation, the red party was not getting a seat, and an extra seat, sorry, and the orange party was getting an extra seat. Now let's think that red party, so party 4 gets one less vote, orange party gets one more vote, and the rest of the parties change in some arbitrary way. Now, what happens is that the seat that the orange party was actually winning in this new situation goes to the red party. So a party was better off by getting less votes. And this is something we don't want. So this is what is known as Alabama's paradox, that can happen, and we want to avoid this kind of behavior. So we want to avoid this this paradox. Unfortunately, it's long been known that this cannot be avoided if we want quota. So Balinski and Young long ago proved that there is no quota compliant method that satisfies population monotonicity. So this is a big problem. So basically, we have to give up on one of the axioms. Or alternatively, we can give up on the fact that the method is deterministic. And this is where I want to jump in. So the next question is, can we actually be quota compliant and population monotone if we allow randomization? And now, if we allow randomization, we have to think of what does population monotone mean. And I'm going to translate this into some slightly different point of view. I'm going to want a method that is quota compliant and that is ex ante proportional. So ex ante, you will get the number of additional, so you will always get your floor of QI, yeah, so your quota, you get it for sure. And now you get more seats with some probability, what probability? With probability proportional to your PI, to your excess over floor of QI. And this can be done. So we have a method that is, this thing, maybe you can move it from here. Okay, better. Grimmett proposed a method that satisfies quota and is ex ante proportional, satisfies proportionality exactly in expectation. So what is the method? The method of Grimmett is the following. So you again assign the floor the floor of QI for every party. And now you look at the residues, you look at these bars here, which represent these PIs, and you place them next to each other in an interval. So if we place them next to each other, we will get something like this. Remember that this would add up to 3. And what we do now is we will randomly shift, we will find basically randomly shift this whole strip. We shift it randomly. Let's say we add a uniform 0-1 random variable, and we look at the points, at the parties that lie under 1, 2, and 3. And we assign those seats. So if we do this, you can actually see that with probability, I don't know, some small number here, this is the shift. This black part here is the shift. And with some probability, then this red party this purple party and the orange party got the seats. And we can do the whole. So this actually was a 0.1 probability. These were the parties getting the seat. Then with some other probability, the shift is going to be a bit farther down. So with another 0.1, we're going to get green, purple, and orange party getting the seats. With probability 0.3, we get some other parties getting the seats. And we can complete the full distribution of how are the final 3 seats assigned, right? So I guess this is another 0.3, another 0.1, and this is the end. Like, yes, yeah, this adds up to 1 at this point, right? All right, so now this is what Grimmett is proposing. Grimmett is saying, let's stick the residues next to each other, do a random shift of this bar, and assign the seats to the parties that lie on these integer coordinates. Good. So however, you can see here that there are like strange correlations happening. I mean, if you use this method there are correlations between what's happening here, between the outcome of the method, right? Between the parties that are getting the seats. So let me explain this correlation in some other example. I mean, in the same example, but like let me paint things differently. So suppose actually the parties were from 2 coalitions, like the red coalition and the blue coalition. Okay, so left and right or whatever you want. So in the original, I mean, for the quota assignment, so for the floors of the QIs, there were 5 red seats assigned and 3 blue seats assigned. So those corresponding to parties 1, 3, and 5, and parties 2, 4, and 6. And this is the distribution that Grimmett tells us. This is the distribution of the remaining 3 seats. Now, under this distribution, it's completely impossible that the blue parties control the house. It's an event with 0 probability. There is no possibility that under none of these outcomes, 3 blue seats will be assigned here. However, if we change the numbers a little bit, so let us change the numbers a little bit. So let me say party 5 gets less votes and gets like a minus 0.6, and parties 2, 4, and 6 get more votes, 0.2, 0.3, 0.1. And now we apply Grimmett's method again. And if we apply Grimmett's method again with the same ordering of the intervals, what we'll get is that now this will happen, right? So, and with this interval, so with this allocation, you can actually compute Grimmett's distribution. And what tells you is that with probability 0.1, the 3 blue parties will be assigned a seat. And with probability 0.9, the 3 seats will go to red parties. So there is a monotonicity problem here that we are observing with Grimmett's method. A monotonicity in a more sophisticated way, if you want. But what happens is the following. Under the original situation, the probability that the 3 additional parties are allocated, the 3 additional seats are allocated to blue parties was 0. So the probability that we select these 3 additional seats two blue parties, we take exactly that set, is 0. Whereas after I increase the votes of the red guys and decrease the votes of the blue guys, the probability of selecting the 3 additional seats from the blue parties goes to 0.1. So, okay, so this is something bad. We don't want this, and we want to know whether there are methods that avoid this problem. Okay, so this is the main research question that we are facing. So in mathematical terms, what we are saying is the following. So we are looking for a rounding rule. The rounding rule is what? Is some mapping that takes a vector of probabilities, numbers between 0 and 1. Okay, so now actually don't even think about this as probabilities, just numbers if you want. Numbers between 0 and 1. Remember that these PIs are the residues. So these PIs are the QI minus the floor of QI. So we have some PIs that add up to some constant K, some fixed number, and we wanna assign K. We wanna find a subset of size K of the parties that gets these seats. So this is my rounding rule. And we want that this is proportional, ex ante proportional. It means that the probability that I select a given I, a given party, a given I, the probability that I is in S in the outcome of my rounding rule is exactly equal to PI. So that makes it proportional. Nice. And this will avoid already population monotonicity. But we want a bit more. We want this selection monotonicity. What does this mean? It means that if I increase my probabilities, my PIs over some set T, so I have some PI primes which are bigger than PIs over T, and decrease it outside T, then the probability that S, so S will typically, as you probably noticed already, will denote the outcome of my rounding rule, right? So this is going to be a randomized rounding rule. The outcome is the parties that the rule selected, right? So the probability that I select set T has to be bigger under P prime than under P. This is a very natural and in principle very weak property, but it's actually not so easy to satisfy. So this is all I want. So I want that if I have some PIs that increase in some set and decrease outside the set, then the probability that I select this set can only increase. And note that here I'm implicitly assuming that T has size K. So this T here is of cardinality K. Good. So the previous example shows actually that Grimmett's method does not satisfy selection monotonicity. It's not selection monotone. And the question is whether there is some method that is selection monotone. And in fact, there are many methods in the literature which are like rounding rules. This is like a very basic property. I mean, it's like in randomized rounding, in statistics, in algorithms, people have studied this for many years. So somehow I have a vector of fractional entries that they want to round randomly to zeros and ones. And as there are many methods, one can explore which of these methods satisfy selection monotonicity. So let's just think about a few of them. So one of the probably most classic methods for rounding is what we know as pie-patch rounding, which was like discovered in statistics and in algorithms sort of independently. And I'm not going to describe the method fully, but to give you an idea of what is the method doing, the method is essentially you take two parties first. So you look, again, we're only looking at the PIs, not at the residues here. So you take two of these residues. So let's say the 0.1 of the blue party 1, and the 0.7 of party 2. And we will assign the whole mass of 0.8 to one of these two parties. In which way? Well, in probability, with probabilities proportional to the sizes. So with probability 1/8, we go and assign everything to the blue party. With probability 7/8, we assign the whole mass to the whatever color, I don't know, green party. So with probability 0.8, we go here. With probability 1/8, we go here. With probability 7/8, we go here. And then we continue. So now we take this 0.8. Let's say we took the 7 with probability 7/8. We took this branch of the tree. We now take this 0.8 against the 0.1 of the green party. And in principle, we could have assigned everything now to the green party with probability 1/9 will go there. And we continue doing this process. Eventually, one of these guys will become 1, and now we assign a seat. So in this case, we did it against the red party. We assign a seat. The remainder of the probability stays in the red party, and we continue the process and say, with some probability, we end up assigning to these green, purple, and orange parties. Unfortunately, this method, which is very natural, also fails selection monotonicity. And this is, and up to here, I've done two things, which are two methods, Grimmett and pipette rounding. And in both methods, there were some choices. For Grimmett's method, I chose the order in which I put these PIs. What happens is that it doesn't matter what order you choose, you will always have this failure of selection monotonicity. So it's not dependent on the order. It's going to fail for every order. And also here, pipette rounding will also fail for every order. So there are examples where you can make it not work. It doesn't matter what order you choose. Another method, which is maybe the most natural method, is what's known as maximum entropy or conditional Poisson rounding. Here what you do is the following. So you want to find some pi's, pi 1 to pi n, so that the probability of selecting a set S of size k, we always select sets of size k, is exactly equal to the product of the pi's. So these pi's can be proven to always exist and are uniquely determined by the p's. This is not completely obvious. This basically boils down to solving a max entropy problem, overall proportional distributions of size k. So this is a natural method in terms that this maximizes some like natural quantity. And here Jamie worked like crazy, and eventually he found a counterexample for selection monotonicity using computational tools. So for n equals 6 and k equals 3, that was the smallest example where a counterexample appears. And if you actually write down this optimization problem, in the end, it turns out that selection monotonicity is equivalent to proving that a certain polynomial is non-negative. So for this n equals 6, k equals 3 case, the polynomial is this one. It's a crazy polynomial. And you can actually, this is a crazy slide, but you can actually make any of the terms of the polynomial to be the dominant term. So selection monotonicity is essentially the same as proving that all the terms of these polynomials are non-negative. And unfortunately, in this case, there is a minus sign somewhere here. Somewhere here, there is a minus sign. And all the rest are non-negative. So, and this, you can actually, I mean, using the fact that there is a minus sign somewhere, you can construct a set of p's that will fail selection monotonicity. And there's, again, are crazy numbers. So these are the p's, the resulting p's from our counterexample. I guess they are simple counterexamples, but simpler in the terms of the numbers, not in size. So I don't think, I mean, we're pretty sure there's no smaller counterexample in terms of n and k. So there is a small perturbation here that in the end makes it like decrease by some tiny amount, 10 to the minus 26 or whatever. But this is done, this was done with like exact solvers. So, okay. So this method is also not selection monotone. There are other methods which I haven't mentioned. So for instance, Brewer's method, and it's also a classic method in statistics that is also ex-ante proportional, that we don't know whether they are ex-ante proportional or not. Sorry, we know they are ex-ante proportional, but we don't know whether they are selection monotone or not. However, there is one method, which is the one we end up analyzing in more depth, which is called Sampford sum. I mean, due to Sampford rounding. It's a very simple to describe, but tricky to analyze method. This is the method. So we're going to select k parties sequentially with replacement in the following way. So we first select the first party we selected with probability proportional to the PIs. So remember that the PIs add up to k. So basically we select party 1 with probability P1 divided by k. Party 2 with probability P2 divided by k, and so on. So we select one party. Then we put it back. So we have party 1. We have selected party 1 or 2 or whatever. At this point, we put it back. And then we choose the next party and the second, the third, and the fourth, and so on, up to the kth party with probability proportional to pi divided by 1 minus pi. So we make it more likely to select things with high p. So if a party has a pi close to 1, then this 1 minus p would be close to 0, and therefore this number will be very big, would be much bigger. If at any point we select the same party twice before selecting k guys, then we just drop it and restart. Okay, and then we do this until we select k guys which are different. There are other ways of like describing this method, but this is probably the easiest to understand, and it's a bit crazy, but this is the method. And what's nice, and this is so Sampford, actually in 1967, he proved that this satisfies proportionality. So this is an ex-ante proportional method. The probability that I assign a seat to party I is exactly equal to pi after doing this. And we can prove, and this is the new result, is that this rounding satisfies selection monotonicity. So this is our main contribution. And I will try, I don't know if Chufei?
Yes?
I don't know if there are questions up to this point.
No, not yet.
Okay, cool. So, okay, so I will try to give an idea of how this is proven. Okay, so first of all, I think it's good to understand what is this quantity. So the probability that I select set A under Sampford. So S is going to be my random outcome. What is the probability that S equals to A? Well, as I was describing the method, I said the first, you select the first guy with probability proportional to pi, and the remaining guys with probability proportional to pj over 1 minus pj. So this basically translates that the probability of selecting a given set is going to be this quantity. And why did I put 1 minus pi here? Well, because here I have A, I have the set, the complete set. If you remove one element from A and take this 1 minus pj outside, it will cancel with this guy, and this pi will be outside. So it's going to be exactly what you actually think. It's going to be pi times the product over the other elements of A of pj over 1 minus pj, but then you can put this back into A and then pop up, and then 1 minus pi goes out. So this is basically the same expression as you would get, which are like, these are the good cases, These are all the possible cases any set of size A could have finished. And this is a rejecting method. I have to do like favorable cases divided by possible cases, and this is going to be the probability of selecting a set. So, and this can be rewritten in similar, in similar ways. Basically, I can multiply everything here by the product of all the 1 minus pj's overall parties, and I get basically this expression divided by this sum. It's a crazy expression, not terribly important at this point, but let me call this expression here f of a. So here I have some f of a divided by the sum of all sets of cardinality decay of these f of a's, f of a primes. So what do we need to do to prove monotonicity? What we basically do is like the very straightforward approach. We take this vector, we take this expression, and we take the derivative of this expression. So essentially you can, it's not very hard to reduce to the case in which I will select, instead of selecting any set of size k, I'm going to think of A being the first k elements, the first k parties. I'm going to increase just one of these parties, and without loss of generality, I'm going to assume it's party 1. And I'm going to decrease exactly one party outside A, which without loss of generality is going to be party n. So I'm going to say I will increase by epsilon party 1, P1. I'm going to decrease by epsilon party n. And I'm going to look at the derivative of the probability of selecting the first k with respect to epsilon. This is the same as taking the derivative with respect to P1 of the probability of selecting the first k guys minus the derivative of with respect to Pn of selecting the first k guys. And we want to prove that this quantity is non-negative. This is actually if we prove this we have proven the monotonicity, because then you can do it by small increments. You can move to any P prime and P by doing small increments. Anyhow, the thing is that what we need is we need to understand the derivatives of this quantity, and this quantity is a ratio of things. And therefore, we need to understand the derivatives of, we need to understand this denominator and its derivatives with respect to P1 and with respect to Pn. Okay, this is not trivial. I don't think I'm going to enter into the proof of this, but I do want to give you an idea on how we can prove proportionality, which is not obvious for Sampford. Sampford paper is basically proving proportionality. And let me try to give you an idea on how do we prove proportionality here. So what we want to show is that for every party, the probability that S contains some party I is equal to Pi. So this is the same as saying, I'm going to use Sampford sampling. I'm going to look at the probability of selecting set A, and I'm going to sum over all sets A that contain I. This has to be equal to Pi. If we write down this sum, we can use the formula we just saw. This f of A is divided by the sum of the f of A primes. And here I'm using A's and B's, but the difference is that in the numerator, I'm going to get all sets A that contain party 1. I can, again, without loss of generality, assume I'm looking at party 1. So I is going to be I equals 1 in my proof, but it doesn't matter, no? And now the trick is going to be the following. So I'm going to say in the numerator, I have all sets A that contain 1. In the denominator, I have all sets. So I'm going to split that part into sets A or sets B. Now I'm calling them B that contain 1, which is the same as this, and sets B not containing 1. So this is a ratio of the form T over T plus Q. So T is this thing, this is T again, and this here is Q. Now, what we will prove is that Q is actually 1 minus P1 over P1 times T. And this directly implies proportionality. Why is that? Because because this was my probability of selecting party 1. Now I replace Q by what the proposition says, and I easily get that this is equal to P1, and therefore is ex ante proportional. So this is what we need to show, and for this, we use a cute counting argument, which is this equation here. So what is the equation telling you? I mean, this is very similar to basically the f of a quantity I was looking before. And what this is saying is that if I sum over all sets of size k, this quantity, I get the same that if I sum over all sets of size k minus 1 over the same universe, no? U is the same universe. So U in principle is my sets of, all the elements from 1 to n. It could be something else, but in principle, think of all the elements from 1 to n. Now, I'm going to get the same if I sum over sets of size k, this quantity, than if I sum over sets of size k minus 1, this other quantity. The only difference here is first the size of the sets, and second that instead of summing over B, over all elements in B, the quantity 1 minus pi, I'm going to sum over the complement over the sum of the pi's. But let me just note one thing, that this looks crazy, but it's not that crazy. I mean, the sum of pi's from over the universe, my universe is going to be 1 to n, is going to be equal to k, right? So this is the same as the sum over u of pi's plus the sum over the sum over b, let's call it b, plus the complement of b of pi's. This is equal to k. And now this guy is of size k. This b is of size k. The cardinality of b is of size k. So basically what I know is that the sum over the complement of b of pi is equal to the sum over b of 1 minus pi. Okay, so basically what I'm trying to say is that this appears is not so strange. I mean, if I had the same cardinality of the sets in both sides, it would be the same quantity. So it would be fine, right? But now I'm moving the cardinality a little. So that's a counting argument that I'm not going to make here, but it's not terribly complicated. Now with this argument, things are actually follow pretty easily. So I take my Q, which was the sum of all these f of b's over elements over sets containing 1. And basically what I do is that I pull 1 outside, and 1 is always in the complement. So I take a 1 minus p1 from this product and put it outside. And now here I'm just multiplying over the others. So the universe is 2 to n, and then b is not considered. After I do this, I use the lemma, the claim there. So I move from sets of size k here. Here, these are sets of size k, which are subsets of 2 to n. I move from sets of size k to sets of size k minus 1 using my claim. And once I move to sets of size k minus 1, I pull p1 back in. Right? I pull p1 back in, and when I pull p1 back in, I include it here, and therefore I have to divide by p1 because I include it everywhere, right? In every set. And that's it. And that's the proof. So basically, this last part is some simple manipulation of pulling 1 out of the complement and then push it back into the set. So now we have that Q is equal to this quantity. We have the proposition we saw before. We proved it, and therefore we're done. Okay, so the monotonicity proof uses some more sophisticated version of this counting argument. It uses a counting lemma, which is like a substantial extension of that, which is this equation here. And I'm not going to enter into the details. And then it uses some probabilistic interpretation of this these sums. But basically, you can actually prove that this denominator of the sum for sampling probability can be written as the expectation of some very simple random variable, which is like a Poisson triad. So it's half of the expectation of this quantity. So, and then with this, you can find upper and lower bounds on this sum. So you find upper and lower bounds on these expectations, which it's the same as the sum. And with this, you can actually write our derivative in a relatively easy way. And then there is some case analysis, and you can actually prove that this ends up being non-negative. But it takes quite some work to do it. I guess the key is this more general counting argument plus the probabilistic interpretation of the denominator of the sum for sampling probability. Good. So selection monotonicity, it's an interesting property, but as I was trying to explain at some point, is that this is not completely satisfying in terms of monotonicity. In particular, we don't know other forms of monotonicity. For instance, we don't know the following. We don't know whether if I increase some probability, so I increase some of the PIs, and I keep another, let's say I increase P1, I keep P2 constant, and I decrease Pn. Now I want to compute the probability of containing P1 and P2, and not Pn. No, so P1 and P2, containing P1 and P2. This, which we call containment monotonicity, is something we don't know. We think that Sampford still satisfies this monotonicity, but we don't know it. So these are natural also. If you think about the apportionment problem, this would be a very desirable property. But also getting these monotonicities is often very hard. And more generally, we have like there are a bunch of possibilities for defining monotonicity. So we have selection monotonicity here. But then we can, instead of going to the residues, we can try to go to the Qs, right? If we go to the Qs, we can define some version of monotonicity that we call threshold monotonicity. That is the following. It's a very strong property that probably it's not easy to satisfy, but we don't know. So threshold monotonicity would be the following. So we set some threshold of seats M, and then we say T is some parties that increase, so get more Q. Then parties outside T get less, weakly decrease, inside weakly increase, outside weakly decrease. Then the probability of T is not necessarily of size K anymore, but the probability of T, some coalition of controlling at least M seats, has to increase. That we don't know. That would be very nice as a property. And even stronger than this is what we call vote count threshold monotonicity. Again, we fix a threshold, but instead of increasing the shares, the vote shares, the Qs, we now increase the number of votes for parties in T collectively, not individually, collectively. And the number of votes outside decrease, of course, right? And this is like the strongest notion of monotonicity we could think of, but unfortunately it's not, it's not satisfied by any method. So this is too much. So this is one of our result is another result we have is that no ex-ante proportional and quota compliant method, even randomized, can satisfy vote count threshold monotonicity. For threshold monotonicity, Grimmett, interestingly, satisfy it, but only for coalitions of size 2, at most 2. So it doesn't in general. And we don't know what does satisfy threshold monotonicity. We conjecture Sampford might actually do it, but we don't know. Okay, so I guess I'm going to leave a few minutes for questions, so I'm going to the end now. So selection monotonicity, which is the property we define here, is not satisfied by Grimmett, is satisfied by Sampford. Personally, I feel it should be satisfied by some other methods, but we don't know more than Sampford satisfying this. It's most methods we try do not. Some methods we try we don't know, and Sampford is the only one for which we know. Vote count threshold monotonicity is out of question, so this is not possible. And now in between there is this threshold monotonicity I defined, and there are other notions of monotonicity that are stronger than selection monotonicity that would be interesting to explore. So this is not clear for me. Okay, so these are, I guess, the main future directions. Are there other notions of monotonicity that we can satisfy either with Sampford or other methods? Or maybe there are other axioms which are not necessarily like related to selection monotonicity that would be interesting also to explore. I mean, these are like kind of open-ended questions, but this is the end of my talk. So thank you very much.
Okay, thank you very much, Jose, for your engaging talk. And now we have Robin for the question. Robin,
Yes,
you get to first.
I'd be happy. I've been listening intently, and I think Jose, why it seems like you want to do this is because you want to present a fair, like people want to perceive this as fair.
Yeah.
And one thing that occurs to me is that when we do see a change in the US around seats in the House election, it's always behind the scenes. They just said Florida got one and Nevada lost one, and that's just how they present the results. I've never heard a discussion of how it happens, which is really interesting. But I don't know if you know in the US, I don't know if you follow our basketball, our NBA.
Okay.
But in terms of this was reminding me of how in our basketball, based on how poorly you do in a particular year, that that helps determine how well where you fall in next year's draft of new players. But there was a challenge in that at some point, if you were doing poorly, you were incentivized to just lose the rest of your games because you would then have a better chance at doing the worst. And so at some point there was actually an incentive, the way that the system was set up, that you actually wanted to not win any more games if you were that bad. And so what they actually did was they went to a lottery. And so depending on how bad you are or how good you are, you actually get ping pong balls in a literal lottery. And literally, when they pick who gets to draft, you get to see the literal lottery ping pong balls. And so that everybody knows that there is this randomness component into it. And so that's where this question is going. And when I was thinking about all of this, is that you're trying to make a fair system. And I guess my question is around how much do you need to explain to anybody around any of this so that they would understand why this system was more fair to something else, and whether people would feel like randomness in this apportionment is more or less fair, or is that just a grounds where they could then, like in the US, everybody gets mad if they don't get the additional seat, and if they had a higher probability than somebody else and didn't get it, I feel like at least in the US they would be trying to go to the courts and they'd be trying to sue and get it. And so that's a lot of backstory to how does this play into fairness, and how do you think you could help use this argument to help people explain whether it's more fair or not?
Yeah, I mean, it's a great question. I do not know of like actual political systems that are using randomness. But there are situations which are maybe not selecting the House of Representatives, but like I don't know, appointing positions in the different groups of a department, where you can think that randomness can be compensated through time. So maybe, okay, so we draw some lottery today, and this, I mean, the fact that you didn't get the position this year maybe gives you some better chance to get the position next year. And I think if you start doing compensating in another dimension, which is time, then maybe it becomes more reasonable and people are willing to take it, right? For the apportionment in the US, actually, it did change. It's not been the same Huntington Hill method for all time. It was Jefferson method. At some point, it did change, and people did observe this Alabama paradox and population paradox. So I think countries do change the methods, but I agree that but randomness is tricky. It's tricky, and actually, most methods that are actually used in the world are not quota compliant. So, and then for drafting in the basketball, I don't know. I would need to understand the problem a bit better, but yeah, I think I don't have a good answer for that.
Yeah, no, if I just kind of follow up for a second, and I think so a lot of systems, when you introduce randomness into it, you can convince the parties that it is becoming more fair. And I think that all of your work is showing that having the randomness can make it more fair. But I feel like exactly to what you point, if it doesn't happen often enough, then people could just feel like they didn't get a good outcome, and they don't get to see the outcomes play out often enough, in which case that's where it becomes challenging to see how randomness does get you closer to fair.
Absolutely, because it's ex ante fair, but not ex post, right?
Yes, exactly.
So absolutely, and if the ex post thing you see it only once in your life, then it's not so fair anymore, right?
Exactly.
If it's every year, maybe okay. I mean, some years I'm gonna be good, and some years I'm gonna be bad. But so yeah.
And I think you have another question, Shafe. Do you want to ask it?
Oh.
I can see it here. I can just ask it. There was a question in the chat that says, does Grimmett's method satisfy selection monotonicity if parties are shuffled uniformly at random?
No, it doesn't.
It still doesn't?
Yeah. It doesn't matter what you do with Grimmett's method. It's not going to satisfy selection monotonicity. It's very crazy, but no. It's not trivial because you have to do a lot of case analysis to prove it doesn't, but no, it doesn't. So it's a very good question. And also the same question applies to pipette rounding. I mean, there are other methods which are sequential and you make sequential choices, right? And then again, it doesn't. So no Grimmett, no pipette rounding would satisfy it, even if you do it in a different order, even if you do it in randomized order or something.
All right, great. Shafe, I think we're running out of time. Do you want to have the concluding thought and thank our speaker?
Yeah, if we don't have any questions in the chat, I think, this is today's seminar. I mean, thank you very much again, Professor Correa, for your interesting talk. I think it also reminds me like how powerful mathematics can be, like helping us with the decision-making and analysis of fairness as well. Thank you very much. And I think just to wrap up, a quick reminder: the session recording will be online already at the website. Also, we have an announcement for upcoming webinars in October. It's jointly with SDP by Emmanuel Bourdon from Bocconi University. And I think that's it for today. Thank you very much, everyone.
Thank you, Shafe. Thank you, Robin.
Thank you.
Great invitation. Thank you very much. Bye-bye.